So our next speaker is Lun Wang. He is a PhD student at UC Berkeley, advised by Don Song. And today he is going to be talking about an efficiency privacy preserving data analysis framework. So Lun, take it away. Thanks.
Yeah, thanks for the introduction, Sarah. Hello, everyone. I'm Lun, and I'm from UC Berkeley. I'm a PhD student advised by Professor Gang Song. And today I'm going to talk about how to build an effective privacy-preserving data analysis framework. So we are living in such an era with unprecedented large-scale data collection. And in this ever-increasing trend of data collection, our privacy is at risk. So large companies are collecting our sensitive information for business analysis or even abuse them for profitable but maybe malicious purposes. For example, in 2018, millions of people's Facebook profiles were misused for political advertising purposes by Cambridge Analytica. So today's collection is heavily based on user consent. So before an application collects your data, it will ask you to check some consent box after reading a long list of terms of services and privacy statement. However, this scheme is problematic in the sense that the users completely lose control on their data once they grant access to data collection. And another drawback is that they can only passively accept the terms, but cannot decide how to control their data actively. And the protection on the collected data today is mainly enforced by privacy regulations. So privacy regulations are crafted by regulators, such as government authorities, and are enforced by law. However, there lacks an effective way to automatically enforce these privacy regulations. And today they are typically enforced via post facto punishment, such as fine, but at that time, the user's privacy has already been compromised. So current privacy-preserving data analysis frameworks can be roughly classified into two categories. So the first category is data loss prevention systems like Google Cloud DLP or Amazon Macy. And these DLP systems are usually provided as a part of cloud storage service and are provided as a solution for small, medium enterprises and startups to comply with privacy regulations. And DLP systems provide privacy protection by access control and de-identification. However, DLP systems are completely controlled by the data collector and do not allow users to customize privacy requirements. And the second type of systems use local differential privacy for specific tasks. For example, Google Wrapper and Proclo are built to crowdsource statistics from end user client software such as Chrome. And Apple uses something called local differentially private count mean sketch to collect emoji usage data. And these systems provide formal user level privacy protection by local differential privacy. But similarly, these systems do not allow users to specify their own privacy requirements. And besides, local differential privacy incurs a large amount of noise and severely harms the utility of the result. So in order to address these challenges, we designed a privacy-preserving data analysis framework called Aegis. And Aegis combines various security and privacy techniques to provide user-specified privacy control. So specifically, it supports automatic policy enforcement, differential privacy, and also preserves the confidentiality and integrity of the collected data. And today, I will mainly focus on the automatic policy enforcement part. So first, let's take a look at today's policy enforcement paradigm. So today's data collection and policy enforcement actually works as follows. So the data owner submit data to the data collector, and the user data is protected by privacy regulations crafted by regulators. And then the data collectors want to conduct analysis on the user's data. And the privacy officer, an employee of the data collector, is responsible for confirming that the analysis actually complies with these privacy regulations. And if the analysis complies with a policy, it will be allowed to run on the user's data. So this approach has two issues. So first, the privacy policies are crafted by regulators such as governments, but not users. So the users themselves cannot specify their own customized privacy requirements. And second, the policies are enforced by human auditing, which is slow and error prone. Oh, sorry. So as the first step in Aegis, we allow the users to specify their own privacy policies and replace the privacy officer with a static analyzer which can automatically check the compliance. Oh, sorry. So our automatic policy enforcement framework, referred to as PrivGuard, is composed of two parts. So the first part is a policy encoding language called PrivPolicy, and the second part is a static analyzer, which can check the compliance of a Python program with a privacy policy called PrivAnalyzer. And first, let's take a look at the policy language. So PrivPolicy is designed following 4 principles. So first, the language should be user-friendly because it will be used by common users who are not essentially experts in programming languages. And it should be also compositional because policies from different sources have to be enforced on a single program, so they should be composed first. And the language should also be extensible because the rapid change of privacy technique, landscape, and regulations. And the language should also be expressive enough to encode most of the necessary privacy requirements. So PrivPolicy first is user-friendly because it is structured similarly to natural privacy policies. So the text above the dash line is part of HIPAA's safe harbor method, and the program under the dash line is its encoding in PrivPolicy. So we can see this one-to-one correspondence between the formal policy and the English policy. And this allows the formal policy to be translated term by term from the natural language version. And second, our language is also conversational. So PrivPolicy is designed intrinsically to be conversational because a policy in PrivPolicy is a collection of policy clauses. And these clauses can be added or deleted separately by different people or groups. And each clause is also a disjunction or conjunction of attributes. So each clause can also be updated conveniently by adding or deleting attributes by different people or groups. And the true semantics is encoded in these attributes. And each attribute contains 2 parts, an attribute type and an attribute value. And these attribute types and attribute values are domain specific and should be designed to capture the core semantics of privacy policies. And the new semantics can be easily added as a new attribute type. So for example, a time to expire attribute can be added to specify before what time the data analyst can access the user's data for analysis. And after that time, the data will expire and be deleted from the database. And currently, we selected 6 attribute types after carefully examining several widely used privacy regulations, including standard SQL operations like raw filtering, column filtering, and redact. And our policy language also allows users to specify their own privacy guarantee requirement, such as difference of privacy or k-anonymity, or other identification techniques. And it also supports standard access control and purpose control. So we encode some example policies from famous privacy regulations, including HIPAA, FERPA, GDPR, and CCPA. And the results show that PrivPolicy is expressive enough to encode most privacy requirements from these regulations. So now that we have this policy language to encode privacy requirements, we can start to see how this aforementioned static analyzer works. So the analyzer is called PrivAnalyzer, and the functionality of it is to automatically check whether a Python program satisfies some policies specified in our policy language. And here is an example of how it works. So here you can see the input Python program imports the pandas library and calls the index function of pandas data frame to filter out all the minor information. And the input policy requires two things. First, all the minor information should be removed before the analysis, and all the zip code should be redacted before the analysis. And the first step of the static analysis is to replace the pandas library with its stub version. And in its stub version, the index function is redefined to remove all the attributes satisfied by this filter operation from the policy. And as a result, this policy's first attribute is removed, and the PrivAnalyzer outputs the second attribute. And the output is called residue policy, representing the unsatisfied attributes from the input. And this residue policy will continue to guard the output until some further program satisfies all the policies, and then the result will be allowed to declassify to the analyst. And in order to illustrate the power of PrivGuard, we collected 23 real-world analysis programs from Kaggle platform, which use a number of different data analysis libraries. And we stub these libraries and design specific privacy policies for each of the programs. And then we run PrivAnalyzer on these programs, and the results show that all the policies are correctly enforced on the real-world analysis program, and the overhead is small compared to the real program execution, typically only under 10%. And we are also actively working on a reference implementation for PrivGuard now. And currently we have an Android app running with Google Fit and Play data sources built in, and an iOS app using HealthKit under development as well. So you can see how to source data from a variety of platforms. And we are also looking at adding Facebook and other social networks as well. And on the analyst side, we have a simple UI and of course a fully featured interface available via the underlying HTTP API. And in fact, I'd like to show a demo of what we've been able to do so far. And I will change my shared screen now. Oh, cool. Cool. Yeah, so on the left is the Android app we have now. You can see it's still very simple, but it's only for a reference implementation. And from this app, the users can import data from other data sources such as Plaid and Google Fit. And they can also specify, you can see, yeah, you can choose data sources from these applications. And you need to log in the application to give the consent. Okay. And after that, you can choose privacy policy from our predefined libraries written in our policy language. So here you can see two policies. They are all toy policies, but we will support more complicated ones in the future version. And after you select the policy, yeah, you can compile the data and policy into a data unit and upload it to our server. So now we have a cluster of servers, and you need to choose a server location to upload. Okay. Then the user's job is done. And on the right is the data analyst panel, data analyst portal for data analysis. And the data analyst can upload script for data analysis. So currently we only support Python. So you can see, yeah, you can see that data analyst choose 2 Python programs. So the first Python program here satisfies all the policies, and the second does not. And we will see how they work differently later. Yeah, and after you submit the data, it will spend some time to run. And yeah, so you can see after some time it will be ready, and you can download the result. So remember, the first program actually satisfies all the requirements. So the result will be directly declassified to the analyst, and he can see everything from the database. And the second program doesn't satisfy the policy. So the result will not be directly returned to him. And instead, the residue policy will be returned to him. So actually here, the policy is saying that you still need to filter out all the minor information before you do your analysis. And this will like guide the data analyst to submit his further program.
How's it frozen?
He's frozen for me. So yes.
Yeah, looks like he's frozen.
Well, let's give it a few minutes, I guess, and see what happens.
Yeah, I guess I got enough time for questions.
Sorry, Lun, we just lost you for like a minute or two.
Oh,
and we can't actually see your screen anymore.
yeah, sorry. Oh, so from which part did you lose me?
I mean, pretty much the end of the demo, I think.
Okay. Let me replay that.
I don't, yeah, not too much.
Sorry about that. Okay. Did I cover this?
Yep.
Okay. So I will continue from here. So the data analysts have uploaded their script and is waiting for the result. And yeah. So after some time, the results will be ready. And because the first script satisfies policies, and the result will be directly declassified to the analyst, and he can see the result in plain text. But the second program doesn't satisfy the policy, so the result will not be directly declassified to him. Instead, he will receive a residue policy. And here the policy is saying that you need to filter out all the minor information before your analysis. And this will get the data analyst to modify his script and do the further analysis. And yeah, actually that's all for the demo, and that also concludes my talk. Yeah, thanks.
Okay. Cool, so we're almost there.
Mm.
Okay, does anyone have any questions? So maybe I'll start with a question. So I'd like a bit more detail, I think, on who the kind of users are. You know, in some of the scenarios, it seemed like this was real, like, end users of systems.
Yes.
And so I guess the obvious question is, do we think that users should be specifying their own privacy policies? I mean, I think users are not very well placed to understand the implications of the kind of choices that they make. So in what contexts do we really want to put that decision into the hands of individual end users?
Yeah, that's a very good question. It's more like a design problem instead of a technical problem. And the approach we are taking now is we provide choices for users. So first, the users can choose to design their own privacy policies if they think they are expert at policy designing and they have some special requirements. But if you are not an expert, you can choose the well-written policies from our libraries. We have already encoded like HIPAA, FERPA, GDPR, and CCPA in our libraries. And these are all well-designed privacy regulations from governments. And we have experts carefully examining them, ensuring that our policy actually covers most of the requirements from them. So these two approaches should ensure that even not well-placed users can even have a better privacy guarantee on their data.
Okay, great, thank you. It looks like we've got two questions from the audience. So Nicholas or Nicola, I can't see your surname, sorry, but if you want to go ahead.
Don't worry, it's Nicholas. I really like the presentation. I have a question. What methods do you use in order to prevent users to upload wrong data? So for example, if I use the system and I am a malicious user and I put my incorrect bank data, is there a way to assure that I am using the right data, or that's just a trash in, trash out problem?
Yeah, that's a very good question. Actually, that's what we are actually working on now. And this involves some well-developed systems called the authenticated data feed systems. And I think yeah, Aegis and his collaborators are also here, and they have two well-known systems, Tankrar and Deco, used to prove to a third party that my data is uploaded from another trusted website. So if we can integrate these systems in our systems, then we are able to ensure that the users cannot fake data because the data is proved to be taken from a trusted website.
Right.
Yeah.
Thank you very much.
Yeah, thanks.
Okay, and Bastian as well, it looks like your hand is also raised.
Yeah, thanks. Yeah, great talk. Very interesting indeed for Utu, because we are building a platform where we indeed envision to give users exactly this power. And so far, this was just a theory from us of how this might be achievable. So that's really great. I think we might actually just adopt it. But what I wonder is, what do you envision how the platform is actually executed, particularly like in a decentralized environment in the context of a DApp? Because if I understand correctly, then this only really works if the program that is running the data analysis is run on some system that is trusted by the user, because you might prove that your Python script is adhering to the privacy policy, but then the user must also trust that that it is only this script that is being run on the data and not also something else. Like some component might copy the data when it's incoming and run some other program on it, also that they use libraries. So you say, okay, you support various Python data analysis libraries like Pandas and PyTorch and stuff. So you also need to be sure that those are the genuine ones, right? And not some substituted forgeries. Do you have any ideas how to tackle that?
Yeah, that's a very good question. So along all my talk, I assume that the data collector is a semi-honest adversary. It cannot deviate from the protocol. But actually, we are also thinking about how to deal with malicious data collector. And this will incur some additional costs. But the current solution we have is, so first, the users encrypt their data with some secret key and give their key to some decentralized key manager. And then all the program execution and the static analysis should happen inside some trusted execution environment, such as Intel SGX or AMD SAV. And so here's the assumption is that key manager is trusted. And in order to make it trusted, we I and my great collaborators from Canal have designed a decentralized key manager system called Chirp, which decentralizes the trust in the key manager to a bunch of nodes. So the trust problem is solved, and then the only way the data collector can touch the data is to honestly run the analysis and the program execution inside the TE, because the user can use remote attestation to make sure that the script you used, the remote libraries you used are honest. And otherwise, they will ask the key manager not to distribute the key to these nodes, and the data collector cannot touch them.
Great, thanks.
All right. Well, if there are no other questions, thank you again, Lun.